We want to start looking at series and trying to prove if a series is divergent or if a series is convergent. And now that we have some background or some sense of some known series, we can start doing some comparisons. So in this case here, it says using a known series, prove that the sum of a over 1 over root n is divergent. So when we're doing comparisons, it is really useful to have a sense of whether the series converges or diverges. In this case, it tells us it's divergent. So when it's divergent, we want to try to compare it to another diverging series. And that way we can see if it's behaving the same or similarly, or if the sums are going to be greater. So since this is divergent, we want to try to compare it to a known diverging series, which is going to be our harmonic series. So if we take a look at a over root n, we can also compare a over root n to r. We can compare that to our harmonic series, a over n. And we know that the denominator is weaker. That means that this term is going to be greater for all n values. Well, if that's the case, we can then start making an argument here. We can say that from n equals 1 to infinity of a over square root n, we know that that is bigger than the sum of a harmonic series. And we know that the harmonic series, this is infinite. Well, if that's the case, then what we can also conclude that this is also infinite, because we know that that sum is greater than the infinity from the harmonic series, so that must also be infinite. So we can conclude that this series is divergent. And we did this by comparing it to another diverging series. So this is a strategy where we're looking at things term by term and making the argument that all terms in one sequence is bigger. That means it must be bigger than, in this case, our harmonic series. So the harmonic series is infinite. Our series that we're comparing must also be infinite. This is a term by term comparison. So for example 2, we want to have a sense of whether this series converges or diverges. So note that we had n equals starting at 2 only because if we start at n equals 1, the log 1 is 0, and we have a 0 in the denominator, so we don't want to do that. But when we look at this, we can see that the log n is a really weak function. And if it's really weak, it's likely to diverge. So a good comparison again would be comparing a over log n, and term by term, that's going to be bigger than a over n, which is our harmonic series. Because the denominator on the left, log n, is always going to be smaller than n, for n bigger than 0. And that means that term by term, each term is going to be bigger. So we can then conclude that the sum of the series of a over log n must be bigger than the series a over n, which is our harmonic series. And we know that, again, this is infinite. So we know that we can conclude that the sum of the series in question is also infinite. And then we can say conclude that this series then must be divergent. Again, this is a term-by-term comparison, comparing it to another diverging series. For example 3, well, it's hard to tell because as that root gets bigger, okay, we're going to get a bigger root. The root n is it looks like it's probably going to be divergent. In fact, it tells us it's divergent. So how can we show that that's a divergent series? Well, in a case like this, we can actually show that this doesn't pass our very first test, our nth term test. So our nth term test, we can test the last term of that sequence, or a infinity, and we know that that's going to be based on the limit as n goes to infinity of a over the nth root of n. Now, if you recall, the nth root of n as n goes to infinity, that is actually now one of the series the known limits that we should know. Okay, from previous, in here, the nth root of n, the limit of that as n goes to infinity is equal to 1. That means then that when we go to here, we know that that limit, this is going to equal a over 1. Okay, that is greater than 0. Therefore, by the nth term test is greater than 0. Therefore, divergent. This must be a divergent series. For this last one, we can show that this is, in this case, probably convergent, because if we take a look at our denominator here, our comparison would be that, well, it's probably going to behave something like the basal series, 1 over n squared. And the sum of 1 over n squared is convergent. It happens to be equal to pi squared over 6. But how can we make an argument here? Well, our argument's going to look like this. Cos n, well, cosine's always constrained between -1 and +1. So we can say that the absolute value of cosine is always going to be less than or equal to 1. Okay, we can actually put an equal to on there. Okay, so we know that if that's true, we can make it term by term, again, comparison, and say that we know that cos, the sum of n equals 1 to infinity of cosine n, and the fact that if we take away the absolute value, it is alternating, this would make it more likely to converge. We know that this is going to be less than or equal to the sum of our basal series from n equals 1 to infinity of 1 over n squared. We know that this is finite. Okay, this has a limit, it's finite. Happens to be equal to pi squared over 6. Okay, we don't really need to know that, but if the sum that we're looking for is less than a finite number, we know that this has a limit. Therefore, this must be convergent. Okay, so this sum must be convergent.